life, but people pointed out that it would cost more to maintain it than it was worth, so it was torn down.
Okay, it's Barry Goodison here. I'm going to interject now because it's now 12:05, and I think it's time for us to get on with today's session. So I'd like to welcome you all here today on behalf of the Ottawa Centre of the Canadian Meteorological and Oceanographic Society. We're currently at 75 participants, and I'm sure some are still going to be joining. And this is our December virtual talk, which in a year ago would have been our Christmas luncheon, but not quite so this year. First, I want to mention that the talk is being recorded and will be posted on YouTube afterwards for the future, if you wish. So just for all of you to be aware that the session is being recorded. The questions, if you have any, and I'm sure some of you will actually be handled through the chat function. So if you're at the bottom of your screen, you should have a little thing called chat. And if you click on that, there's a place where you can type in your question. And Ada Lowen will be sorting through those questions, and she will provide the question to the speaker. That way he can leave his presentation up there in case he has to go back and refer to something, and he doesn't get bogged down in trying to read questions. So that's how we will handle it, rather than the individual giving their question verbally. If something happens and we lose you, stick around, because we'll be working on fixing it. We've had a couple of situations where that happened, and we were successful in sorting it out. So I'd like to turn now to Don Conway to introduce today's speaker. Thank you.
Thanks, Barry. Well, several years ago, a leading Canadian Arctic researcher was asked by some politicians why his predictions of climate change and their impact in the North should be believed. And he simply responded, "You don't have to believe me." He said, "In a few years, you'll see irrefutable evidence for yourselves." I think our speaker today would agree with that. Derek Mueller examines the indicators of impacts of climate change in the cryosphere and the consequences of a warming climate on cryospheric systems, such as ice shelves, glaciers, sea and lake ice. And if not for the pandemic, this summer, at the end of July, he would likely have been up on the Milne Ice Shelf when it broke up and took some instruments away on an ice island. The breakup of the ice shelf was an extraordinary event, but I think he would say it was not unpredictable. Dr. Mueller is an associate professor at Carleton University and co-director of WHIRL, the Water and Ice Research Laboratory in the Department of Geography and Environmental Studies. He's been involved in helping develop the Canadian Ice Island Drift Deterioration and Detection Database. I'm sure there's a shorter acronym for that. And also a contributor to the Canadian Science Advisory Secretariat's review of a new marine protected area at the very north of Ellesmere Island, and with a name I hesitate to say because I'm sure I mispronounce it. He'll be talking to us today, and we're delighted, on the collapse of the ice shelf. We may also talk about the life within the ice shelf, and the consequences of a warming climate on cryospheric systems, such as ice shelves. So thank you very much, and over to you, Derek Mueller.
Thank you very much. That's great. You've done your homework well, and looking up my activities. So let me go to my first slide. So this is a satellite image of the Milne Ice Shelf breakup from the past summer, and I promise I will talk about this in my talk today. But I've worked along this coast for 2 decades now, and I want to use this opportunity to tell you what we've learned in this remote environment, and that will put these recent changes into context and give you a little larger view of what's going on, rather than talk about a 2-day time window where the breakup occurred. And I'm sure you'll agree that there's some fascinating aspects of this area. And what I'm going to tell you today really represents a team effort of my colleagues and students, supervised, co-supervised by myself and other professors. And I would thank them now for their contributions in advance of this talk, but also we'll list them later on at the end of the talk. So today I'm going to give you a quick overview of ice shelves and on Ellesmere Island, give some definitions and background, that kind of stuff. And then I'm going to go into the Milne Fjord research that we've been doing. I'll talk about the ice shelf breakup, of course, and then I'm going to talk a little bit about the last ice area and what that means. So starting off with a quick cartoon here of what ice shelves in the Arctic are like. So ice shelves are thick floating ice or land fast to the coast, so they're not drifting away, and unless of course there's a breakup, and then they form ice islands. So you can see this ice island splitting away. They gain mass from freezing on the underside. They gain mass from snow falling on the top side, but they also melt on both their top and bottom sides. In the Arctic, there's sometimes glaciers that flow into these ice shelves, but not so much, especially recently when some of these glaciers are no longer reaching the ice shelves, or those ice shelves that have broken up and they're left with only a glacier and no real ice shelf. So this is quite a contrast to what happens in the Antarctic, when there are really the continent is glaciers flowing in all directions and out over the ocean. And so 40% of the coastline in Antarctica is really an ice shelf, and they're quite a bit thicker than the Arctic ones. And just one last point before going on, the ice shelves on Ellesmere Island formed thousands of years ago, but they're not a relic of the last ice age. So they really started their life when there was a cooler period in around 5,000–6,000 years ago. So that's an important distinction. Where are they? So in red, I've circled the ice shelves in Ellesmere Island. So these are the only ice shelves in Canada. And there are some in northern Russia as well. And then I've circled in yellow ice tongues. So an ice tongue would be like an ice shelf in that it's floating thick ice, but it comes from a single glacier and it flows out in a fjord. So Peterman Glacier, for instance, could be considered an ice tongue, although some people call it an ice shelf, because at the end of it, there is that floating thick ice. But regardless, ice shelves and ice tongues both produce these massive tabular icebergs called ice islands when they break up. So another important concept that we're going to talk about today is the notion of an epichelf lake. So these are formed when there's space between the ice shelf and the landward side, the coast, if you will. So in a fjord, and you can see here with a map of Milne Fjord at the bottom panel, there's a glacier that flows in, Milne Glacier, in through the fjord. It doesn't actually join with the ice shelf, and instead there's a space here of ice. It's actually perennially ice covered, but that ice is super thin. It's only 1 to 2 meters thick, and it's lake ice because of all of the water that drains from the snowfields and the glaciers as they melt in the summer. It comes in through the watershed and it piles up behind the ice shelf. Here you can see a cross section of the fjord, and the ice shelf is blocking the exit of this fresh water, and it impounds in behind. And at the bottom of this, there's a steep gradient in salinity. And I think it was Victor who mentioned John Keyes, who was one of the people who was the first to really look at the oceanography in Disraeli Fjord, which is a little further along the coast. And Andrew Hamilton, I think, is here, and he is the first to really look at the oceanography in Milne Fjord. So we have, that's the sort of a very rare occurrence when people get up here and do oceanography. So it's kind of exciting to talk about it. So speaking of oceanography, here are some CTV profiles. So if you lowered a salinity instrument into the water in these fjords, you would see that it's absolutely fresh and drinkable water. And then at a certain point, you start to transition to full seawater, and that's at the bottom of the graph here. You can see full seawater, and so the halocline, or the separation between the fresh and the salt water is very abrupt, and you can see that by this horizontal line. And another thing is that the temperatures in the top part of the water, where the fresh water is, are often quite warm, several degrees Celsius. And in the top waters, you can get species that live in freshwater or brackish water, like this little copepod here. It shares the same water column as the marine copepods. It's brothers and sisters from the ocean, but instead of being, in a lake on land and having the marine cousins offshore in the ocean, it's upstairs, downstairs in this sense. So they're sharing the same water column, which is quite unusual. So it's like a vertical estuary in a sense. And what we've thought about over the years, and this comes from the work of John Keyes and others, is that the salinity profile, you can tell where the bottom of the ice shelf is, the draft of the ice shelf, by looking at where this freshwater layer ends. And in fact, that's actually not, there's some subtle issues with that are not, that we didn't understand before. And I'll show you a little later on what we're gaining more knowledge of this system and refining our understanding. So that's more or less true, but not always so. And I'll show you that in a minute. The ice shelves along Ellesmere Island have reduced by 95% in their area over the last 100 years or so. And I spent a lot of time digitizing remote sensing imagery in a GIS to delineate all of the ice shelves along the coast. In 1906, I used somebody else's interpretation of Robert Peary's journal. When Robert Peary went around this coastline, he described this ice that's undulating, which is it perfectly describes ice shelves. And so we have some notion as to how big the ice shelves were 100 years ago. The first air photos were in 1959, and then we have happened to have a spy satellite in 1963 that passed over. We have spot imagery in 1988, and then in the radar era, so when ERS, the European radar satellite, one of their first, and RadarSat 1 and 2, I digitized using those satellite images. And you can see here these step changes when I would, of course, these horizontal lines just mean there's no information between the beginning of this line and the end. But when we have new information, you can see big step changes or cliffs where we have a reduction in ice shelf area over time. And as we break up ice shelves, sometimes that liberates an ice tongue, that's a glacier that's singular and flowing out into the water, and then the ice tongue extent goes up in the record. And so we have sort of these curiosities in the record, but all that to say that we've had a drastic drop in ice shelf area over time. And if you want to see that in a map format, because I'm a geographer, I like that sort of view. And we see 1906 here. This is, anecdotal evidence. So we're not really sure of the mapping of this necessarily, but that's what one can imagine the ice shelves might have looked like. And then in the 1950s, air photos derived maps. Here you have the ice shelves there. And then over time, you can see the ice shelves, it's the dark blue areas, by the way, in case you're wondering. And the green are fragments or pieces that are loose. And the ice tongues are in cyan, so they are sometimes growing and then breaking up themselves. And my record goes to 2015. I have started digitizing further to fill in the last 5 years, and that is ongoing work. But these are data are available if anybody wants to download them. They're free online, so that publicly available. Now, one sort of question about the ice shelves would be, well, what about climate change? And Don mentioned this in the introduction. And you can see here warming of the global atmosphere over the last 130 years or so, 40 years, I see. And this is the warming that we're all upset about, and you know, there's a climate emergency and so on. And I'll note that well, I teach statistics, and at the second year level sometimes, and I tell my students a little bit about you know, how to lie with, or there's how to lie with graphs. There's a publication out there, and this is one way to lie with graphs, you know, or mislead people. You can see that there's a lot of white space, and my axis is quite wide here. So I've actually minimized the change in the global climate record here, and you might think there was something going on, but I did that for a purpose, and that is to overplot here the Arctic climate change. And as you probably are all aware, the Arctic is warming at twice, or in some places 3 times faster than the global climate. And so that is well illustrated by this red line here. And if you think about when the ice shelves broke away, well, we're not totally sure when these happened, but sometime probably in the 30s or 40s, there was that massive change from Peary to the mapped ice shelves. Some big calving events happened in the 1960s, the 1980s, and now they seem to be happening quite a bit more frequently. And the notion here is that with warming, we're exceeding a threshold, and the ice shelf can't sustain itself anymore. It's melted, thinned to a very vulnerable state. And when you sort of crest the threshold of temperature, then you see these effects. However, the devil's in the details. It's not always clear cut. And you can see here a cooling period in the 60s when there was major calving. So it's not that straightforward. And I've spent some time really trying to think about this and tease out what are the processes that are important here. So I'm going to transition now to the Milne Fjord research site and introduce you to that area. And the first paper I'm going to mention is Colleen Mortimer's work. She was a student of Luke Copland's at the University of Ottawa, and she did her master's on radar surveys of the Milne Ice Shelf. And at first, these lines were started when Luke and I and actually Andrew Hamilton, who's also on this call, were hosted by the Canadian Rangers on a sovereignty patrol. We were I think the first embedded scientists in a ranger patrol, and it was a really exciting opportunity for us to skidoo along the northern coast of Ellesmere, much the same as Harold Serson and Victor did back in the day. And that doesn't happen very often because we're usually using planes and helicopters. So it was a neat opportunity in celebration of IPY. So that was 2008. And Colleen came up the next year in 2009 and finished the survey. So every squiggle here is driving around with a skidoo with a radar on the back. And you can see from the thickness, well, you probably can't see it, but 90 meters is deep red, and 10 meters or less than 10 meters is this green. So the Epishelf Lake here has very thin ice, only 2 meters thick maybe. And then the ice shelf on average is about 55 meters thick. And what Colleen was able to do was to pull some records from the 1980s and determine that there was a thinning on average of about 8 meters of ice over that period from the 1980s to 2009. So that was a very important data set. Next up, we have Adrian White's PhD thesis. So that she was a student of Luke Copland's at University of Ottawa. And here are the ablation stakes. So we come every year and put an ablation stake into the ice and come back and measure it and see how much is melted out. And that way we can figure out how much ice is lost on the surface of the ice shelf. So we're looking at the surface mass balance. And I don't think it's any surprise that the surface mass balance here is, well, predominantly, except for 1 year and one part of the ice shelf, it's negative. So there's just losing ice over year over year on the surface. There are 3 bars for every year here. And the reason why is that we've parsed it out between 2 parts of the ice shelf. There's an outer unit here where you see these long blue lakes and rolling topography and clean ice. There's a central unit back here, which has chaotic undulation, so that's not as regular as the outer unit, and dirtier ice. And then behind there's what used to be called the inner unit, where it was thought that the Milne ice shelf was actually thicker, but now we understand this to be really a thin ice of lake ice, the epishelf lake. So the takeaway here is that the outer unit, that's in blue here, has almost every year has a more positive, right? It's not positive, but it's more positive or less loss than the inner unit. So, or sorry, the central unit. So the red bars are always longer, downward pointing here. And the average of the two, the area weighted average, is the gray. So overall, the ice shelf is thinning, there's no doubt. But the thinning happens more at the back of the ice shelf, at the rear of the ice shelf, and not so much at the outer side of the ice shelf, which is interesting. And that is sort of corroborates, there was mention of Fritz Kerner, he had always said that there was a sort of climatic effect of the coast where there's a lot of fog rolls into and hits the shore, and there's a lot of stratus cloud and fog at that site, and it basically makes that outer edge of the coast conducive to growing ice. And indeed, the ice shelves in Canada are the only place that I know of where the equilibrium line altitude, the elevation of equilibrium, can be at 0 meters above sea level, so roughly at sea level. So that's kind of a special place, although nowadays that's clearly not true because we're in a very mass negative regime here. Now, we've been talking about thickness and we've been talking about the surface. So there's obviously a relationship between the ice mass gain and loss and the atmosphere, but because the ice shelf is really at the interface between atmosphere and ocean, it sits in between, we have to also consider the underside of the ice shelf as well. And here is Andrew Hamilton's mooring that he's put in, or at least the top of it. It goes down from there about 350 meters to the bottom of the fjord. And at the start, we put in about 24 instruments, mostly temperature instruments, but also some salinity instruments. And it's been running more or less in situ here since May 2011. And so this is my question to you, Victor, at the end of the talk. I'd love to know if there are any other longer running moorings in a Canadian Arctic fjord, and maybe you did some work out of Tanqueray or d'Iberville or something that's longer than this. But what Andrew was able to do with this mooring, because we weren't there over winter, and now we could see what's going on in the wintertime, we see the epishelf lake here in the warm colors. basically, after we leave for the season, it actually grows downwards. The epishelf lake expands into the, pushing down the ocean water, and then over the winter, it starts to drain away. So the water is leaving the fjord underneath the ice shelf, and so that's an important distinction. So when we're thinking of the draft of the ice shelf, we have to account for this effect, the seasonal effect. So that one of the questions that came up about the ice, this epishelf lake and this growing of this freshwater layer and then shrinking again is, well, how is it getting out under the ice shelf? And it could have just been going out everywhere under the ice shelf, but it seems like there is a particular concentration of this outflow, and we went looking for it. We had a suspicion that it was this feature here. You can see on the satellite image across the ice shelf, there's a feature in the ice, and there's also one here as well, where the ice looks thinner. It's sort of like a divot in the ice, and this is it here. And if you go to the air photos, you'll see them in 1959. They've sort of always been there as well, as far as we know. And so we went looking at the cross section of this purported channel, and Jill Rayevich here was a master's student of mine, and took a radar similar to the one that Colleen used, but we walked over the channel back and forth many times. You can see these squiggles here where she went back and forth over several sections of channel, and tried to look at the morphology of it. We were thinking, well, if there's water flowing, it's going to look like a river valley, right? Where there's a V, but instead of a river downgrading into the land, it would be upgrading into the ice. And so we saw evidence of that. And you can see the radar gram that she had developed here, and she picked where she was confident and ignored some of the garbage or returns that she couldn't interpret. And you can see here the shape of the channel. So that was really interesting. And then we found some open openings in around the channel, and we're able to lower down a current meter. And so this is somebody's hand here lowering a current meter. And what's interesting is, well, you lower an instrument, it's the rope is going to be straight down like a plumb, and lower. And then all of a sudden, the rope starts to vibrate violently, and it's pushing off to the side, and it's pushing off to the downstream side. And this is then the deflection of the rope. And what's happening here is we're in a jet of brackish water. So here's the epishelf lake would be very fresh water, and it's going underneath this channel, in through the channel. It's mixing with the salt water below. It's causing a brackish layer, but it's also jetting out of the fjord underneath the ice shelf. So this was an important discovery. So knowing this, we were very excited to actually go in, because we couldn't find a big enough hole to lower instruments in. I had to buy a hole melter. This contraption here basically heats up water and melts a hole that's about a half a meter wide. And we drilled or melted down 10 meters through the channel apex here, expecting basically to be able to lower instruments all the way down to the bottom of the fjord. That would have been something like 400 meters below us. And so here we were going to put moorings in and current meters and that kind of stuff. So that was the setup here, and here's Jill's profile of the channel. But what we did is we got in, and Andrew was and Drew were there at the beginning, and they used this little ROV. It's a little hobby grade, remotely operated vehicle, a little robotic submarine, and they lowered it down through the hole, and they came across an ecosystem of benthic animals. So you see these brittle stars and worms and the sea anemones and all sorts of scallops, all sorts of things. And we were able to make a video. If you click on here, or I guess you can't click on a Zoom call, but I can probably copy this URL into a chat, and you can see basically a 7-minute video of the dive down underneath this ice, through 10 meters of ice, through 10 meters of water, and then down under the ice shelf. And you can see here, this is Jill's data that we thought was just going to be open to the ocean below, but somehow there is a horizontal bench. That's where we landed this ROV down on top of, and we don't know how it came to be there. Either it's a tunnel here where the water is jetting through the tunnel of ice, or it's some kind of horizontal bench that's protruding out from the side of the channel. So we see that the ice shelf here in gray, and the ocean here in white. So this was a fascinating discovery, and to my best of my knowledge, nobody's ever described animals of this nature inside an ice shelf like that. So and I'm just gonna wrap up this section of my talk here, just to say that well, everything's connected. This is a diagram by Andrew's thesis, and it's really busy, and I'm not going to explain everything, so that's because it would take too long, and I like it busy because it shows you how much we have to learn about this system. There's so many processes that are ongoing in this fjord, and there are really two end members, right? There's the atmosphere that's warming the ice from above, and there's the ocean that's warming the ice from below, and they're both changing, obviously. And there's everything that's going on inside the fjord. And so now, really, all of the people working in this environment, the Milne Fjord system, are interested in understanding how everything interconnects. We have an ocean, an ice shelf, an epishelf lake, a glacier, and a watershed. And, you know, for instance, the watershed, if there's a warming climate, the watershed is there's going to be more melting, and then there's going to be more runoff. And then what does that do to the epishelf lake? What does that do to the fjord oceanography? What does that do to the ice shelf when it's jetting out underneath this channel, and so on? And one of our, and so we're doing remote sensing. This is, I like Chris Dirkson's talk earlier on this fall. He talked about the three-legged stool, remote sensing, modeling, and observations in situ. And so we're doing all of that in our work. And I'm just showing you little pictures here of some of the instrumentation that we just make on our own, little radiation shields, for instance, with the 3D printer, and a custom-made climate logger here, which actually sends its data to us. So that's been helpful, and that's a GPS on the glacier. So we're looking at ice motion, grounding line dynamics. We're looking at mixing in the epishelf lake and the fjord below. We're looking at runoff from the watershed, and the discharge of the entire fjord into this channel that you saw, and the fjord oceanography through the mooring and CTV cast. So all of this stuff is ongoing every year that we can get up here. And of course, we couldn't get up this last year, and John alluded to that. I mean, we wouldn't have been there at the time of calving of the ice shelf, but it did break up, and we unfortunately we couldn't retrieve our instruments that were out on the ice shelf. That all that ice left and took the instruments with us. So more valuable than the actual instruments themselves is the data that were on them, and we couldn't download them in time. So that's a shame. And the ecosystem as well. The benthic animals that were that I showed you in pictures also were part of the piece that broke away. So we don't know whether how much of that is left, if anything. And you can see here the change in the ice shelf. So in the 29th of July, an intact ice shelf, or nearly so. I mean, there's still lots of rifts and changes that have occurred on this ice shelf over time. And you can see it broke off along this weak part here, and then it connected to another rift that had been growing since 2013. Just across the way here, but it didn't break along the channel, which was something of a surprise to me anyway. I thought that the channel was really going to be the weak part. So that's interesting. It didn't do that. And when it broke up, Adrian White, who did her PhD obviously on the ice shelf, and I've showed you her stuff, and is now working at the Canadian Ice Service, and of course is looking at these radar images every day, and super interested obviously in the ice shelf, and spotted it right away. So we knew that this had happened, and we got together some material and put out a talked to the media, and of course it made a splash in the figurative sense, in the media, that is, and lots of coverage internationally. If you're under 30, this might mean something to you. It went to the front page of Reddit, so that was exciting for my grad students, and also Greta Thunberg retweeted some of the coverage. So it's been definitely looked at from the climate change angle. And actually, just before I go on, I forgot to mention, and it's maybe something worth noting, that all of those changes in the ice shelves that I showed you in the background section of my talk, and the changes in the temperature over time, remember that anthropogenic climate change really took hold only in the last say 5 decades or so. So a lot of the changes that have occurred on these ice shelves in the beginning of the last century are not necessarily due to climate warming, or predate are due, perhaps obviously due to climate warming, but not necessarily anthropogenic climate warming that really came online in the past the 1960s or so. And so that's just an interesting distinction to make. And I always think about how natural climate warming might have brought these ice shelves to a precarious state, to maybe the edge of a cliff, for instance, and then humans came along and altered the climate that much more, and we gave it the last shove off the cliff, if you will. So here's the Adrian's view of the ice shelf breaking up. I've got a website as well that explains some of this in context. And here is everybody wants to know, well, what was contributing to this breakup event, and if you know, please tell me, because I don't really have any really firm understanding of what happened, why it broke up now in particular. Here are a couple ideas. There were high winds in early July. And that's, you see this red area here. So Adrian White sent this to me, and there was this high winds too early on in time to really affect the breakaway of the ice shelf. But what it managed to do is push away a lot of sea ice from the front of the ice shelf. So this image here, satellite image, you can see a lot of open water. And that's actually quite unusual for this coast. Usually the ice is pushed up quite tight against the coast here. And so that open water then just allows the ice shelves to wander off into the Arctic Ocean if they are broken up. And they were, and there were rifts already previously known that propagated. And Brad Lewkowski is somebody who's working on this, modeling the rift propagation. He used to be at Harvard in the States, and is moving now to University of Washington. So he's working on rift propagation modeling to understand how the breakup occurred. There's this ice being pushed away from the shore. Kent Mueller from the University of Toronto talked about this in ArcticNet, or the Arctic Change Conference last week, about how that was a contributing factor. Some people have noted that meltwater ponds on the surface of the ice shelf drained away suddenly, and maybe that water went into cracks and was able to widen them out so that they split, that sort of thing. The actual breakup happened when there was wind that was offshore, and that's kind of important, to something to push the ice out, although the wind wasn't too terribly strong. This is a diagram of the wind being pushing offshore here, if you see that in the bottom corner. And this, I'm sorry this panel didn't work out. I will actually just blow it up here, so hopefully you can see this data from our automatic logger that's collecting temperature. It's on the Milne Glacier, so it's not really at the ice shelf. It is about it's the closest actual measurement of temperature that we have, and you can see here other years where we've measured temperature at the same location. So we're comparing apples to apples. 2019 was a warm year here, and then there was an outage in that sensor. So it continues on over here in the record, but actually you can consider it's probably actually much warmer than that indicates because of this artifact. So it was 2019 was a very warm year, but 2020 is also a warm year, and you can see it here. Right up to the last record here is on the July 31st of every year. So we've got 2017 in red. We've got 2018 in this brownie color. And then there's 2019 in this blue color with that artifact. So we're really not, we're truncated there. And then 2020. So you can see, and these are, by the way, cumulative positive, it's positive degree days. So every day that you have a temperature over 0, you add that number, and you accumulate those degree days until and write down the number here. So that gives you an idea of the melting power of the air, the heat in the air. Now, as the ice shelf broke away, of course, there are now ice islands in the Arctic Ocean, and here we have pictures of that Adrian White took or traced from radar imagery. You can see these ice islands scooting around in the Arctic Ocean and in the current, and now you can see the ice broken up here on the side of the shore, about 190 kilometers away to the west from where Milne is. And so these ice islands, we would love to go and put beacons to track their motion over time. They are fragmenting into lots of pieces, but Adrian White is digitizing every one of them that she can see, and that is contributing to this database that Dawn mentioned at the beginning of the talk, the Canadian Ice Island Drift Deterioration and Detection Database, or CI2D3, which is also publicly available, although Adrian's stuff will come later as she has to keep working. They haven't stopped drifting yet. And now I'm gonna take a sort of a broader view and back away from the Milne Ice Shelf for a second and talk about the coast of, well, I call them the planet's most northerly coastline, which really starts here in Greenland and goes along the northern coast of Ellesmere Island and across the northern coast of the CAA, the Canadian Arctic Archipelago. And this figure here is illustrative of a certain phenomenon, and that is that there's a lot of pileup of ice along this coast. The currents circulate in such a way to bring the ice to this area, and as it piles up, it ridges, and then there's more thickness. Or if it keeps circulating there, it will thicken even if it's level ice, undeformed. And so you get what basically you get a preponderance of multi-year ice in this area. And then it's much more longer lasting than first year ice. And this has always been the case and has been predicted to be, or always been the case, at least in the last on record, and predicted with climate projections to be also a place where it will continue to be the case. However, it's not immune from change. So even though we have projections into the future that this will be where the ice will be, you know, even when there's an ice-free ocean, there should be some multi-year ice along this coast until even that melts. So it's maybe the longest lasting area of ice. It's certainly still vulnerable. And then since it's vulnerable, the World Wildlife Fund, WWF, has been advocating to preserve this area as best as possible. And I mean that because there's obviously local things you can do to preserve areas, but there's also a need for global conservation, and that stems from reduction of greenhouse gases, as we all know. Their push was the last ice area. It was this huge bubble here that you see on the map. And it's been really interesting to see how much of this area has been conserved for various means. There's the Taliruptu-Imanga National Marine Conservation Area here in Lancaster Sound that just came into being. The Pikila-Sorsuaq area here, the North Water Polynya. And now the Tuvaluituk Marine Protected Area north of Ellesmere Island. This is an area the size of Poland, and it was enacted into a temporary protection regime. So it's got a protected status for 5 years, so starting in 2019. And this protects the Milne Ice Shelf and the Milne Fjord because it's a marine protected area. So that's everything that's up to the high water mark. But it doesn't protect the watershed that we see as being critical to, you know, as in interacting with the fjord and the ocean and that sort of that nexus of terrestrial and marine habitats. There's, again, Dawn mentioned this report. It's out now, the CSAS report. If you're interested in knowing more about this area, then that's a link to click on. But what's missing, again, just thinking about the marine protected area, which is a spectacular thing, and wouldn't want to take away from it, but it doesn't protect these ice-dependent ecosystems that are on land. And here's an example here. My former PhD supervisor, Warwick Vincent, has been studying the Walker Glacier, which is pictured here, and has found endemic yeast, or at least as far as we know, it's endemic. It hasn't been discovered anywhere else. So it may be found somewhere else one day, but for now, it's the only habitat for this particular kind of yeast that is cold tolerant, cold loving, actually. Here's a picture of microbial life on the Markham Ice Shelf, which is now drifted away. Little organisms that are in the water, ctenophores and so on, that are associated with the water column under multi-year ice, for instance. So cryoconite holes on the Milne Glacier here, lakes that are perennially ice covered but are now becoming ice free. And of course, my friends from the underside of the ice shelf that you've seen already. So all of these ice-dependent ecosystems are worthy of conservation, if in the sense that they are rare, and we're just really beginning to understand how they function, or even just discovering them, like the one under the ice shelf that we found recently. And the other important thing is that there are also primarily microbial, or at least very small organisms, right? So instead of charismatic megafauna, we have an uncharismatic microfauna or something along those lines. It's not as easy a pitch as a polar bear or a walrus or something like that, but also worthy of conservation. And they're at the bottom of the food chain, after all, so they are very important. And Warwick and I wrote a piece in one of these perspectives, or it's like a kind of a commentary in the journal Science, and wanted to get these ideas out into the public to pitch the idea of, well, we have these amazing conservation areas. Tuvalu-Wituq is huge, but it really doesn't extend as far to the east and as far to the west as you might want if you're trying to preserve the last ice area. So we need international cooperation to extend beyond these borders. We need to capture both the marine and the terrestrial environments in these protected areas. And of course that we need not just the local conservation, which is useful in a sense so climate change is obviously one of the major issues here, and it's the elephant in the room, if you will. It's important, obviously, to reduce the greenhouse gas emissions so that we can lower the temperature and preserve the ice. But even so, as ecosystems are dealing with this major stressor of climate change, they also could have other stressors, right? Like mining operations and boats transiting and disturbing habitat and so on. So if we can reduce all of the multiple stressors in this environment, and it's easy to do because there's not a lot going on commercially or up in this particular area, so it's easy to commit to these protections. Then we will help those ecosystems be more resilient. And also having a big green blob on the map in the northern part of Canada is great, because people will look at that and say, well, I wonder what's going on there. And it will increase awareness, and people will understand more about these special Arctic environments. And so I'm at the end. I'm just going to conclude by I guess this is exactly what Dawn said. I mean, massive changes are underway in the Arctic, and this is all related to our warming climate. And Milne Ice Shelf breakup is just one example of many, many, not just ice shelf changes, but glaciers, sea ice, permafrost, you name it. I will remind you again that the Milne Fjord is a system, and it's really at the the ice and the ice shelf is between the atmosphere and the ocean, and influenced by both. And the fjord is the coastal environment between the open ocean to the north and the watershed and all those processes to the south. And so these are important connections and ways of thinking about the environment. And lastly, that we need these rapid conservation efforts. We have these really unique and special ecosystems that we're really only just finding out about, and we need that local and global conservation to mitigate that. And as I promised, here are all the people who've helped me out. So thanks to them, and thanks to you for your attention. I'll just point out that the top row here are all of the professors and researchers that I work with, or who haven't even come yet to the ice shelf. I'm actually, Luke is really one of the only ones and Greg have come up, but they're all a part of the team. And here are grad students that I've worked with and who are still working with me on various projects. Current grad students and undergrad students on this line, and then former students and field assistants and so on the bottom line. And of course, all of our work takes a lot of financing, as you can imagine. So I'd like to thank ArcticNet. Go Ice project is run by Luke Copland, and it's an ArcticNet project that funds this work. And the Polar Continental Shelf Program is absolutely instrumental in getting us to our site, and we couldn't get along without them. So that's a shout out to them. Thank you. And I'm free to take questions.
Thank you, Derek, for your excellent presentation and putting together so many different concepts on ice, islands, and glaciers, and the atmosphere and ocean, and how they're all connected, and ecosystems. It's a lot of information to cover, but you really broke it down and made it easy to understand. And it's also really interesting to see all the fieldwork that you're doing and how excited you are about all of this. So thank you so much. As Barry mentioned at the beginning, if you have any questions, you can post them in the chat box and I will read them out to Derek and he will answer them. And I don't see any now, but maybe Victor can answer Derek's question that he posed earlier about if there are any other longer running moorings in the Arctic fjords.
Not to my knowledge, although you have to respect that my experience up there was some time ago. But that's certainly a wonderful continuity to have and so useful in this research. And is there any way to go out and retrieve any of that instrumentation that got lost on the parts of the shelf that floated off?
It would be a needle in a haystack, I think. I can't imagine how we would find it. Next time we go up there, we're putting beacons on all of our instruments, so we can at least go to that spot and look. But I'm not sure we'll find them ever again. And just to your last point about work up in this area, as far as I know, the oceanography, it was the 1970s was really the last time that anybody had done any work except for Martin Jeffries, who I know well, and came after and worked with Harold Surson. And then since then, I think it's really people that I know and have worked with in these fjords anyway.
Sure. If I can ask a verbal question. So you mentioned that this protected area doesn't extend inland. Who's the authority over the extent of that protected area? So
the marine protected area it's DFO, and so Department of Fisheries and Oceans. So that's part of the problem, is that you know they have no mandate on the land, and so that's where their map is drawn to that limit. So it's a bit of a bureaucratic issue in that sense. However, Parks Canada is also involved in these discussions, and so they have the authority to bridge go past the coastline. So they might be able to step in and make a bigger conservation area as opposed to just the marine.
Right. If I can mention, I'm sure you're aware of all of the work that was done by Jeff Hattersley Smith, who traversed that northern coast by dog sled in the late 60s, early 70s. So in some of his work, I recall, he had predicted what we're seeing now. I mean, and he could see it just in the scope of his glaciological work. And really a phenomenal researcher and contributor to the science. So some excellent people. And so is Martin Jeffries, who worked, as you know, as you just mentioned, with Harold for many years up on that coast.
Yeah, Hattersley Smith's work we're well aware of, and it's interesting because there was a bit of a downturn in the temperature just after he was doing his work, and things just sort of settled out for a few years, and then they started to accelerate again. So we are seeing his his predictions come true for sure.
Well, look, I'd like to compliment you on a wonderful presentation. It's really quite fascinating. And somewhere we'll find where this is recorded that we can access it, because I'm sure there's some people I could like to send it on to. And I'm also impressed with you carrying on a long tradition of creating novel new instrumentation to serve the purposes of your science. It's that goes back to John Keyes's days and Harold's days, and it's great to see. So really fascinating with what you're doing there on the instrumentation. It's really key to obtain those measurements that are so essential. And thanks again for a wonderful presentation.
Thank you, Victor. I have a question for Derek. Were there any strain nets on the Milne Ice Shelf? And thank you for the great talks from Peter.
So we do have some GPS measurements, so high precision GPS measurements at the ablation stakes that we measured. So when Luke and Adrian and Andrew and I went out and put these stakes in, every year we come back and then measure exactly where it is, so we can tell how much it's moved apart. And Greg Crocker has done a bit of work on that, looking at the displacement over time. Does that answer the question?
Sounds like it does.
Good.
Thank you. Question from Sean on the water balance. It's interesting how the lake deepens in the winter months. Is there subglacial runoff adding water in the winter months, or is this driven from below, from mixing from the fjord?
That is the probably runoff from the watershed, so surface runoff, not subglacial. Although I think Andrew Hamilton would be the best person to talk about that. He has it on his fingertips, whereas I have to lift these things up. So Andrew, if you're there, maybe you could chime in.
I think Andrew is here.
Yeah, I'm here. Thanks, Derek. Good question, Sean. We think so. In the summer, it seems like the vast majority of the change in depth of the epishelf lake is coming from surface runoff inflow, but there's certainly subglacial discharge coming out from the bed of across the grounding line of the Milne Glacier at the same time. And we have a paper in review right now that shows how there's a layer below the epishelf lake, kind of in that halocline, that also varies seasonally, which is most likely due to this subglacial discharge coming up from at depth. But for the most part, it kind of seems like the two layers are a bit separate. So the epishelf lake is surface runoff, and then you have this kind of layer below the halocline that is subglacial runoff. What's happening over winter is a little bit of an unknown, of course, due to lack of observations, but for the most part, we think probably the hydrological system shuts down to a large degree over winter. I wouldn't say that with 100% confidence. There's always the possibility of like a subglacial lake drainage or something like that. So that would be something really cool to look into, but that's the best we can answer right now.
Thank you, Andrew and Derek. Another question is about the navigation hazards of drifting ice islands. To what extent is this a problem? And related to that, what are the draft of these ice islands?
So the ice island drift as a hazard is not at this time not a big issue, but it could be in the future, and there are a couple scenarios. So first of all, we've studied the Petermann Glacier, which is flowing into the northern like nearest Strait area, and ice islands from the Petermann Glacier come. So that's between Greenland and Canada, and they come down to the east coast and could potentially take out an oil rig, for instance, on the east coast of Canada off Newfoundland, and that's a major concern. There used to be concern when Dome Petroleum, for instance, was out in the Beaufort Sea, whether ice islands from the northern part of Canada could come into that area, and that's downstream of the ice shelf. So that's actually quite a likelihood in that sense. Now there are no major infrastructure offshore of the coast of Alaska and northern Canada that would be at risk in that sense. But there was an incident actually a few years ago where an ice island was embedded in a multi-year flow and drifted down into Eureka Sound. And actually, they canceled the sea lift that year because the ice island was blocking, or potentially would block, the passage of the ice breaker. There's no way an icebreaker is going to get past an ice shelf or an ice island like that, which leads me to my next answer, which is the draft of the ice island would be in the range of something like 50 meters or so. I think the latest thickness measurements we have are about 80 meters, so maybe not quite 80 meters thick, based on a little bit of melting over that time, but in the range of 50 meters to 60 meters draft, or maybe even a little bit more, depending. Give you an idea.
Great. There's a follow-up question about the strain nets. Did the GPS data indicate any hints of the breakup?
We haven't looked at it carefully enough to know whether it now those data are just once a year, right? So we would see changes, sort of on an annual resolution. Maybe Greg Crocker is around and can answer the question, because he did look at it.
I saw Greg here earlier. If you want to unmute yourself, Greg, you can try to answer.
Oh, hopefully that worked.
Yeah, we can hear you. Yeah.
Yeah, I can't really answer the question. I haven't looked at the last couple years, but up to about 2018 or so. And the flow was generally to the north and fanning out a bit, as maybe you would expect. But I haven't looked at any kind of convergence, divergence, or stresses and strains or anything like that. So I've mapped vectors of flow, but that's about it. So I don't think I can really say, or at least maybe I can say that there was nothing obvious to me apart from the general expected pattern of movement.
Thank you.
Thanks, Greg. And Frank had a comment about lakes in Ontario. There are 14 years of continuous under ice data available from a lake in Ontario that could potentially be an introductory project for a student unable to go to the north. So, and idea about that, maybe someone can get in contact with him if they're interested.
Yeah, that's cool.
Yeah. There's a question about the history and scope of the ice lab at Carleton. Marie's a Carleton geography grad from the early 80s, and there are only a few of us studying sea ice. So do you want to give an overview of our lab, Derek?
All right. So our lab, the Water and Ice Research Lab, is well, there's myself, I'm the ice person, and there's Murray Richardson, who is the hydrologist. He's the water person. So together, we've joined forces and have a lab with, I don't know, we have about 5 or 6 students each, and have been in existence for 10 years now. And you can find out more on our website. It's world.carleton.ca, and there's a map of where we've done work and other information there. And if that's not enough information, we can always take an email, no problem.
Yeah, I'm a grad student in that lab as well, and I study sea ice, not the glacier stuff. It's pretty good. John, during the IGY and before several islands were occupied. Do you know if any of them are occupied now?
No ice island has been occupied. I don't think there's the same tolerance for risk as there used to be back then, and also the ice islands don't seem to be holding together for very long either. So, so while there was in that era where there were lots of ice shelf ice island camps, there's nothing going on as far as I know.
Great. I don't think I see any more questions at the moment. I'll maybe put a plug in again about the video that Derek mentioned about the life inside Milne Ice Shelf. I think Frank posted a link to that in the chat at the beginning. It's I've watched it a few times. It's very interesting. I definitely recommend checking that out.
Just a comment. So, Derek, I suppose that means that without having good ice islands, there's no more flights with twin otters to the North Pole as Weldy Phipps did back in the late 60s.
Oh, they do it, but they land on sea ice, so they find a good flow that's reasonably solid, and then they put fuel cache out on that, and so it's just it's a sea ice flow at that point.
Can I comment? It's Denny Burke here. I'm hosting the meeting. For those of you who have seen all these websites be posted on the on the chat stream, if you want to make a copy of this before we close the meeting, there is a box that shows up with three dots in it on the bottom of the chat area, and you'll find in there a way to save the chat to your computer. And that way you don't lose it. But you can do it now because they're all posted earlier, and then you don't lose them.
Great, thanks. There's a question from Andrew. Do you think the hydraulic head from the Epichelf Lake could have played a role in pushing the ice island offshore, given that it was a big melt year with lots of meltwater filling up the Epichelf Lake this past year?
We have thought about the hydraulic head for many years and have endeavored to measure it, but we can't figure out how to do it properly. It can't be so. It could be a contributing factor. But we wouldn't. I'm not sure how to even tackle that question. So you have any ideas, that would be great to hear.
I think that's all the questions I see so far. If anyone has any last minute questions, they can type them into the chat now. But maybe if not, I'll pass the mic back over to Barry and thank Derek again for his great presentation.
And thank you, Ada, for dealing with all questions, and that's great. Thanks.
I'll just thank everybody that's still on the call. I mean, you've kept people glued to their seats with a very interesting talk. I just want last thing I wanted to do is again remind you it'll go up. This will be posted on the CMOS YouTube channel. So if you just even in Google just type in CMOS YouTube channel, and it should bring up not only this talk when it's posted in the next day or so, but the previous ones as well. So you can access them and watch them at your leisure again. And I just want to mention about our next talk. It'll be 21st of January. It's going to be Dr. Konrad Jezewski at University of Ottawa talking about Holocene climate variability of the North American Arctic and impacts on terrestrial ecosystems and human populations. So it should be a very interesting talk. Should note that both Derek and Konrad are longtime CMOS members, and which we're very pleased about, and I encourage anybody else who would like to join up to go to the website and take advantage of that. So hopefully we'll see many of you again in January, and we have talks scheduled every 3 to 4 weeks right through to the end of April, and those are regularly posted on our website, the Ottawa Centre portion of the CMOS website, where you can find out information. And so again, thank you, Derek, very much for your talk. Really enjoyed it. And thanks to everyone for participating, and have a good day. Take care, everyone. Have a good holiday.
Thank you, everyone.
Thank you.